I'm John Fincher. I am the Tech Talk coordinator for Coding Nomads, and I have with me our co-founder, Ryan Desmond, who is right up there, top center on my screen. He is going to be doing our next talk in our series on data structures and algorithms. This is kind of the computer sciencey part of the courses that come up. This is really good information for folks to have. Makes you a more capable, a more marketable programmer and coder. And so Ryan is going to be talking about, last time we talked about arrays. This time we're going to talk about linked list and some of the algorithms that are there. So without further ado, I'm going to turn this over to Ryan. Take it away.
Thank you, John. Hello, everybody. Thanks for joining. Today, as John mentioned, we are going to be discussing the linked list, and I've made a bit of a slideshow here. So we'll go ahead and jump into that. When we talk about the linked list, it's really difficult for me to not also kind of mention stacks and queues. So this talk will be about the linked list almost entirely, but ideally towards the end, we're going to have a little bit of time to show how a linked list is also a very perfect data structure to very quickly modify to make it a stack or a queue. So what is a linked list? A linked list is an abstract data structure. And what I mean by that is that it's an idea, right? In programming, we oftentimes have a lot of, take the array, for instance. The array is a collection of contiguous places in memory where we can store a collection of data, right? And it's this data structure that's quite oftentimes, for instance, in Java and many other programming languages, it's created for us, its rules are set out for us, and we just kind of use it. When I say abstract data structure, it's a little bit different because an abstract data structure is an idea about how we want to organize data and store data and essentially iterate through data. And we can create the rules that we want and enforce them, right? And the linked list falls into that category of this data structure where we're actually just, it doesn't really exist in the world, right? It's something that we create and essentially set up rules and then enforce those rules so that it acts in a certain way, right? It most simply, or kind of in the most basic kind of explanation of what a linked list is it's simply a list of elements where each element points to the next list. This differs from an array in a sense because an array is just this big collection of data. And let's say that we've got 10 elements in this array. I can just say, give me the fifth element, give me the second element, give me the ninth element, right? In a linked list, that is not the case. A linked list is just one element that has a reference or a pointer to another element. It's that simple. And that next element may or may not have a reference to another element. And that next element may or may not have a reference to the next element. And in a singly linked list, which is the most common form of linked list, each element, or what we call nodes, have a reference to one and only one other node, if it exists, right? So a linked list is not indexed, right? It doesn't have index of 0, 1, 2, 3, 4. It just has this idea of a node, which is an object that may or may not point to another node, right? And that process just repeats and repeats. The data in a linked list is not stored in contiguous memory, right? And so this is just kind of a fun fact about it. A linked list typically consists of objects that we call nodes, and the nodes can be stored all over memory in your machine. But we have this idea of a reference pointer, again, where each node may or may not have a reference that points to another node somewhere else in memory. And that other node somewhere else in memory may or may not have a reference that points to another node somewhere in memory. Depending on how you use your linked list, depending on which operations you're performing, one of the upsides is that they can be extremely fast. And as I mentioned here in this slide, I say O of 1 or O of n, that's talking about big O complexity, which essentially measures the complexity of our algorithm over time with a kind of infinite sized data set, right? So with a linked list, imagine that we've got 3 nodes that are all linked 1, 2, 3. If I want to add a new element to the front of that list, all I have to do is just pop it on there, pop that new node onto the front of the list. And it doesn't matter if that linked list has a billion elements in it. The idea of adding one new node to the front of it will be what's called constant time, or O of 1. It will be extremely fast. It does not matter how long that linked list is. It will not affect the speed or complexity of the operation to add a new element to the end. Inversely, if I was going to add a new element to the end of a linked list, then it would be O of n, or what's called linear time. The complexity of that algorithm will be as complex as that list is long, right? So if I've got 3 elements in my linked list and I need to add something to the end of it, right, it will take 3 operations to essentially get to the spot where I need to do that insertion. And if I have a billion elements in that list, it'll take a billion operations to get to that spot where I can insert the element at the end of the list. And that's what the O of n stands for. That being said, most operations such as insert, find, get, remove on a linked list have the complexity of O of 1 or O of n. So typically, as long as you're using it properly, it's very, very fast, right? As I mentioned before, it can also be very nicely used as a stack or a queue. It just lends itself really well, and you'll see that in a moment. There's a couple different types of linked lists. There's the singly linked list, and that's just where the linked list just moves in one direction, right? Node A has a reference to node B, which has a reference to node C, but node C is completely unaware of node B or node A, right? It's a singly linked list. It just moves in one direction. There's also this idea of a doubly linked list where A points to B, B points back to A, but also to C. So B can have a reference to the previous node as well as the next node. That's called a doubly linked list. So it basically nodes are aware of not just the next node that might exist in this list, but also the previous. And then there's also this idea of a circular linked list, which kind of will wrap around back to the front when you reach to the end. One other thing about a linked list, today I'm going to be doing most of this discussion in Java. But you can create a linked list in any programming language, and they are used in every programming language. So just because I'm going to be using Java today does not mean that we can't be doing this in Python or C or C# or JavaScript or whatever it might be. Linked list is an idea of how we can store data in memory that you can do with any programming language. So this is kind of the idea of what a linked list looks like, right? Some of you might have seen this picture in my Slack or forum posts, but these blue dots here are essentially the nodes. And then a node is an object. And you'll notice inside the node that it says T data. And in Java, what that T stands for means it's generic, right? And a linked list typically are generic. We can have a linked list that stores numbers or strings or cars or trees or whatever we want, right? It's a generic data structure. And so we can put any type of data in it. And then each node also has a reference to the next node, right? So this node here at the front, which we also call the head of a linked list, which is very important. The head of a linked list, essentially, if we lose track of that head of the linked list, we lose the whole list, right? So we never want to lose track of the head of this list. But the head points to this first node, which points to the second node, which points to this third node, fourth node, fifth node, and so on. Again, all of these nodes have no idea that any of the others exist except for the next one that it points to, right? With a linked list, as well as with any common data structure, there's a couple of core operations that we need to be able to do, right? We need to be able to create the linked list. We need to be able to add data to that linked list. We need to be able to get data out of that linked list, and we need to be able to remove data from that linked list. And then two kind of nice helpful functions are to be able to quickly check the size of that linked list, as well as determine whether that linked list contains an element that you're looking for, which is just really a nice utility method. Very oftentimes we're checking to see if some data structure that we're currently working with contains an element that we're looking for before we try to get it, right? And in this talk, time permitting, I'm going to try to walk us through, and we're actually going to live code, fingers crossed it works, all of these methods into a linked list. So first, we have this idea of, and we're going to kind of skip over creating a linked list. That'll be self-evident. The first thing that we're going to be able to need to do is add an element to a linked list, right? And just to kind of give it a graphic, here I'm saying linked list.insert front, right? And so in this case, the method that we're thinking about is a method that will take a node of data and insert it into the front of the list. And so how would we do that conceptually, right? And so in this little diagram, these 3 nodes down here are the existing linked list. And we've got this idea of a head node, which is a reference that points to the first node in this list. But I want to insert a new node into this list. And this is where linked lists get kind of fun, right? It's how we navigate, insert and remove everything, data into and from the list. But what I need to do is essentially with this new node, I need to say new node.next equals head, right? So whatever the front of the list is, I need to say new node.next equals that, whatever that head is, right? So head is just a reference that points to this first node. So I'm going to say new node.next equals head, or the node that head currently points at. And so head, still will point here, but we've got this new node that also points here. So then the next thing that we need to do is point head to the new node, right? And then our linked list is, we've completed this insertion, right? Where we got this new node, we pointed its next reference to the previous head in this list, and then we redirected head, or the reference to head, to the new node, right? So before we dig too much into some of the other operations, let's just go ahead and open IntelliJ and kind of dive into this and create our node class and a couple of basic things and get our insert front method working. So, all right. So
Okay,
I've got, go ahead.
this is worth the price of admission. Seeing you live code. This is where it could all go horribly, horribly right.
Yeah,
So
let us pray. The beauty of a
let's
live
go.
demo. It almost
There
never
we
works the first
go.
time, but so I've got this empty package here, and I'm just going to call it linked list. And inside this package, I'm going to create a couple of classes, right? And the first class that I'm going to create is simply going to be the node class. And this idea of a node, it's just a simple Java class that will hold a bit of data, right? This is going to be a generic class, right? And if you're not familiar with Java already, all this means is that this node class, or the data that it will be able to store, which we call tData, can be of any type, right? This could be a string, this could be an int, this could be a char. Well, technically it can't be an int, it could be an integer, but it's a generic class so that we can use it with any kind of data type. We don't want to have to create a custom linked list for strings and a custom linked list for integers and a custom linked list for chars, right? We want this one linked list to work with every different data type that we have available. And then we're going to have this idea of the node next. And at the end of the day, this is kind of it, right? We're going to build a couple constructors, but this is the kind of root of a linked list. This class that has this, it holds some data, any kind of data, and has a reference that points to another node. This is the same class, right? This node object may or may not point to another node, the same class type. What I'm also going to do in here is create a constructor that takes a tData, and I'm going to say this dot data equal data, and this dot next equal null, right? And all this does, when I say this dot data refers to the instance variable of this class, and this data right here refers to the parameter that was passed into this constructor. So when this constructor is called, it will set the data for this node, and it will set this dot next, or the reference to the next node, to null because it does not exist. Something that can also be really helpful with linked lists is overloading the constructor and taking in your tData, but then also taking in your node next, right? And we'll see why this makes sense in a minute. And I'll do the same thing. This dot data equal data, and this dot next equal next. And that's it. That's our node class, right? The next thing that we're going to need, and this will probably make a bit more sense in a moment, is, and I could, just to demonstrate, let's call it the linked list main. Just muting a few folks here. Let's call this linked list main. This is going to be the class that has our main method, where we just test things. So right now I could already say node of type string, let's call it n1 equals new node. And let's have it say hello, right? And then I could say node of type string n2 equals new node. and I'll say world. Then I could say n1 dot next equals n2. I've just created a linked list, right? It's that simple at the end of the day. And it gets more complex, but at the end of the day, that's all a linked list is, right? And then I could say something like, just to be really redundant here, node n3 equals yay. And then I could say n2 dot next equals n3, right? And what I've done here is created a linked list where we have node 1 that has the data hello, right? And it has a reference to called next to n2, right? And then n2 has the data world, and it has a reference to n3, right? So what we've just done is essentially we've created this simple linked list uh, just like this, 1, 2, 3, where they all point to each other. That being said, we want a bit more functionality than that. So we're gonna go ahead and not go there quite yet. And we're gonna create a class that actually has a bunch of utility methods that help us interact with this idea of a linked list. So I'm just gonna call this custom linked list class. And in this custom linked list class, we're gonna have a couple of methods such as like add, find, remove, size, contains, etc. Those methods that I mentioned that are helpful or kind of useful operations on a linked list. But the first thing that we're going to need, and the most important thing when dealing with a linked list, is this idea of the head node or the first node in the list. Because if you have a reference or if you have the ability to find the head node, you have the ability to then start iterating through the rest of that list. If for some reason you lose that reference to that head node, you lose the whole list, because without the head, without the first node, you can't get to the second node. And without the second node, you can't get to the third node, and so on. So it's really important in a class like this that you have this idea of a head node, right? Next, I'm going to create a constructor called custom linked list. And I'm going to get kind of fancy with it. I should say this is also a generic class. And I'm going to use what's called var args, so that this constructor can be called with one or more nodes. And when it is called with one or more nodes, it will essentially start to build that linked list. So this var args simply means that I can pass in 0 or more nodes and into this constructor, right? Variable length arguments is what this is called. So here I'm going to say if data.length is less than 1, then head equal null. It just means we're creating an empty custom linked list right now. We're not going to do anything. We're just creating this object. We don't have anything else to do yet. Else, if data.length is not less than 1, then I'm going to iterate through it. I'm going to say for int I equals 0, I less than data.length, and I plus plus. Then I'm going to call my add method, which does not exist yet. I'm going to say data at the index of I. And this is a little interesting here. I'm going to just go ahead and create this add method so we don't have that error. But right here, we're saying data at the index of I. When we're dealing with var args, just as a little Java lesson for folks, when we're dealing with variable length arguments, which is this dot, 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 as soon as we're inside this constructor, Java treats that data element or that parameter as an array, right? Because it can have 0 or more elements, 0, 1, 2, 3, 4, up, nearly infinitely in the amount of elements that could be passed in. Not that you would want to pass more than 3 or 4 or 5 things into a constructor like this. But this is why we say data at the index of I, because once we're inside this method or constructor, Java treats this var args parameter as an array. So basically, for as many elements as there is in this array called data, I want you to call this add method and pass in each piece of data, right?
Hey,
Now go ahead.
Ryan, when we're processing var data here, could we also use a for each loop there?
Totally.
For item
Yeah,
and item colon data, that kind of thing. Okay.
exactly. You could say because this is generic.
Could be T data or T item
Key
in data.
item in data.
Yeah.
And then we could
Would that
use
work?
item.
Yeah.
Yeah, I think that would work. So this is
Okay.
another, so this is called a for each loop where we can iterate through each element of a collection, such as this data array.
Right.
Um,
And so, yeah, and so Python users, that's a straight up, for item in data kind of loop
uh-huh,
if you wanted to do that. Okay. Thank you.
exactly. Yeah. So now we're in the add method, and this is kind of the back in the presentation I was showing you. We've got this idea of a new node, and we need to add it to the list, right? And if the list doesn't exist, so pretend all three of these nodes down here don't exist, we've just got this new node, and we don't have any other elements in that list. That's the first thing that we need to check for. So I'm going to say if head equal null, then I'm going to say head equals new node, and I'm going to pass in data. And this is kind of where some of that magic happens, right? Because the user passed in, they didn't pass in a node object, they passed in the string hello, right? Which is this data. And T just meaning it can be anything. It could be an integer, 12. It could be a string, hello. It could be a car. It could be anything. And we're calling it data. But they passed in, let's just use strings for now to keep it simple. They passed in the word hello. And so we're saying, great, we can go ahead and add that. We're managing this as a linked list. And because it's a linked list, we have to have this idea of a next node or a next element, which is why we created this node class. So we'll create a node and we'll put in for T data, we'll say data equals hello, the string hello. And then we'll essentially add that to the linked list. And in this case, if head is null, then we're going to say head equals new node, right? And that node will contain the data. Does that make sense? Am I making sense so far? Cool. So otherwise, if we hit this else block, it means that head is not null. That there's already data in this linked list, right? And so here we have a couple of choices. And because we're the programmers, we can do this in a variety of different ways. One of the fun things about a lot of these data structures is that they're just ideas and we can implement them however we want, right? So I'm going to, just to make it real simple in the beginning, let's start with an addFront, or like add to beginning, right? So if this linked list is not null, and I want to, meaning there is already data in it, and I want to insert something into the beginning of that list, which is, again, constantly fast, constant time fast. If there's a billion elements or 10 elements, they're going to take the same amount of time, right? Then I'm simply going to do what we talked about over here in this presentation, which is I'm going to get this new node and I'm going to point it at whatever the current head is. And then I'm going to point head at this new node, right? So first thing I need to do is say node, let's call it new node equals new node with data in it. So we have this idea of this node that contains the data that the user wants to add to this. We're going to say new node dot next equals head, right? So now we've done this, essentially this part right here where we're pointing the new node at what is currently head, right? And I'm like pointing at my screen like you guys can see that. So the new node dot next currently points to whatever the current version of head is. And then we'll say head equals new node. It's that simple. And then by doing that, we've done this, where the head used to point at the previous first node, but now it points at the new next node. And that works because before we did that, we said new node dot next equals head. So new node dot next points to whatever is at the front of this list. Once we have that relationship or that reference established, then we can switch head, right? If we didn't do that, like let's just say we said head equals new node, if that head currently was the first node in a list of a billion elements, right? And we said this line, head equals new node, we would erase that existing list and we would have a list with length one, consisting of just this one node. Does that make sense? Cool. I'll take that as a yes, but please feel free to ask questions here in the chat or to interrupt me. I'm going to move kind of fast through here and I'd love for you guys to be able to for me to speak as little gibberish as possible. So that's it. That's all we need to do to add an element to the front of a list, right? We say new node equals new node data, new node dot next equals head, and then head equals new node, right? Let's also, just while we're here, let's do an add to, let's say add to, or like addEnd, right? Let's say that in this particular implementation of our linked list, we want to be adding elements to the end of our linked list. And there might be a use case at work or whatever, for whatever reason, where that's necessary, right? The same beginning, if head equal null, right? We still need to check that always, because if there's nothing there, all we have to do is say head equals new node. Boom, we've got our linked list. It has one element, which also happens to be the head element. If head is not null, that means that there is data in this linked list. Then what I need to do is actually create an iterator. And I typically just call it iterator. And I say node iterator equals head, right? And then with this iterator, I can now iterate through the linked list using this iterator without having to modify or in any way alter this idea of the head node. And so then I'm going to say while iterator.next does not equal null, iterator equals iterator.next. And this is kind of funny. And when you're dealing with linked lists, there's always a lot of .next, next, and you'll see that that gets even more so. But what we're doing here is we're setting this variable iterator to whatever head is, or whatever head points at, right? And then we're saying while iterator.next is not null. So if this node points to another node, then this node equals whatever that next node is. Iterator equals iterator.next. So if I had A that points to B and B that points to C, and my iterator is currently on A, I would say A equals whatever is A.next, which is B. So iterator becomes B, right? And we're going to keep iterating until iterator.next is null, at which point we'll have reached the end of the list. And then I can just say iterator, there's a number of different ways to do this, but I can say iterator.next equals new node data. Right? Because when we've exited this while loop, we can be absolutely sure that there are no more nodes in this linked list. Does that make sense? Because when iterator.next is null, it means we're done. We've reached the end of the list. So then I can just say iterator.next equals new node. And now we've just added that new node onto the end of this list, or we've added it as the .next element to whatever node is at the end of this list, right? So now we've got the addFront, addEnd methods. Let's go take a look at what we're going to want to do next. So retrieving an element from a linked list. So now we've been able to add things to this linked list, both to the front and to the end. It's also possible to add things in the middle if you want to. You could do a sorted linked list, or there's a number of different things that you could do. But in this case, we want to, for instance, we just want to get something out of the front of a linked list. Like, let's say we're treating this like a queue or a stack, or I should say like a stack, where we're only accessing the whatever plate is on top of the stack, right? So with a stack, you basically push things onto the top of the stack and you pull them off the top of the stack. Just like if you had a stack of plates, you'd add a plate to the top, or you'd remove a plate from the top. That's called a stack data structure. And so we want this idea to be able to get back whatever node is currently at the front of that linked list. So let's go try that. So I'm going to create a new method that returns the data, not the node, but the data. So this is going to be public T, let's say get front. And now all I really have to do, and we have our choice. Do we want to, we could also say like popFront, meaning I want to get the first element in this list, and I actually want to remove it from the list. Like when I want to consume it out of the list, right? So here, the first thing I'm always going to do is check if head equals null. If head equal null, return null. Like we've got nothing to return. This list is empty. There's no point in us doing anything. If head is not null, meaning that there is data, then we need to we always need to pay special attention to this idea of this head element. We want to make sure the head is pointed at the next node before we delete the current head node, right? So I'm going to say, how about node return value equals head. Then I'm going to say head equals head.next. And then I could say return value. Dot data. What doesn't it like here? Provided object required type T. What can I do? Cast a T. That'll do it. So essentially what we're doing here is I'm grabbing that first node. I'm calling it return value, whatever the head currently is. I want to grab that and I'm going to save it in this variable called return value. Then I'm going to change the head to point to the next one, right? And then I'm going to return this return value, which is what was previously the head value. And so this kind of goes right along with this idea where I want to get this first node, but this is also the node that head currently points at. But in order to do that, I essentially need to save this value, whatever this current value is. I need to save it in some kind of variable because I'm going to need it later. Then I'm going to point head to whatever is the next variable or next node in this list. And then I'm going to return this node back to the user, right? So our list that was previously 4 nodes is now 3 nodes and 1 going back to the user, right? So that's essentially exactly what we're doing right here. We could also do the same exact thing for if we wanted to pop off the end of the list, right? We could also do a read method or a find method that doesn't actually return the value or returns the value without deleting it from the list, right? The a more interesting form of removing, right? Because if we're removing from the front of a list or from the end of a list, it's pretty straightforward. But a much more interesting problem is how we remove from the middle of a list, right? And so let's say that we've got this linked list here. It has 3 nodes. We've got this head node that points to the first node in the list. And for whatever reason in our particular linked list, we need to remove an element that's currently in the middle, right? So what we essentially have to do, we've got 1, 2, 3. We essentially have to say head.next equals head.next.next. And this is the actual syntax that we'll use. And so that'll essentially bunny hop over this node so that head now points to whatever the next dot next pointed to, right? And what this does is it effectively deletes this node out of the linked list. And then for instance, in Java, because Java's garbage collector will kind of just, crawls around memory looking for objects like this that don't have any pointers or references to them and automatically deletes them. But removing an item from the middle of a list is definitely a little bit more interesting. So let's create a general remove method that will remove something from a list no matter where it's found, the beginning, the middle, or the end, right? So let's just call this remove, and this will take in that same T data, whatever it is. Let's say they want to remove the word hello from this list. Again, the first thing that we need to do is say if head equal null, return. There's nothing to do, right? There's no list, there's no data in this list, therefore we can't remove anything. Otherwise, the first thing I would check is head.data equal data? Meaning, is the data that they're trying to remove the first thing in the list that is currently head, right? Then if so, I might just, essentially do the same exact thing that we did right here. I could even call this function right here. I could just say popFront, right? And in this case, we don't really care about the return value, but that will do exactly what we need to do, which is delete the first thing off this list, right? If head dot data does not equal data, like if let's say I've got this list that has hello in the first node, world in the second node, and yay in the third node, and I'm trying to delete world, right? Then head dot data equals hello, but the data being passed in is world, right? So this is not the case. So otherwise, I would say I got to do the same thing where I start iterating through this list. So I'm going to say node iterator equals head. And while iterator.data does not equal data, we're going to just iterate. Iterator equals iterator.next, right? And if we want to, interestingly, if we want to delete something out of the middle of a linked list, right, we also have to keep about this idea of what was the previous node, right? So something I'm going to do here is actually create another kind of variable just for us to deal with called previous. And I'm going to essentially say previous equals iterator. And what this will do, and this will make sense in a moment, but as we iterate, I don't want to just always pop to the next node and forget about whatever previous node I was on, because we need to do this idea of kind of knowing which node we were coming from and which node we're trying to connect to. If I just iterate along the list like we did before, I would not, and we're currently on this node that needs to be deleted, I don't have a reference back to the previous node so that I can link it to the next node, right? So I have to keep track of this previous node. So while we iterate, we're going to say previous equals iterator, and iterator equals iterator.next. And it's a little bit funny when you're first playing with linked lists, but it's actually a little bit graceful once you kind of start wrapping your head around it, right? Once we've exited this while loop, we know, and I could also say and iterator dot next. Well, I'll do that actually. I'll come back to that. When we've exited this while loop, we know one of two things, right? We know that we've either found the iterator, found the node that contains the data that we're looking to delete, right? Or we've reached the end of the list, right? Which is something that we should actually just handle. I'm going to take that back. So I'm going to say and iterator dot next does not equal null. So this will keep iterating while the current node does not have the data that we want in it, and the next node is not null, right? So when we exit this list, or when we get out of this while loop, we can know that we either have found the node that has the data that we want to delete, or we've found the end of the list, and there's really nothing else to do. So I'm going to check the easier one first. I want to check if we've found the end of the list, right? So I could say if iterator dot next equal null, and I could also say and iterator dot data. Well, I don't think we need to do that. Then we could just say return null, right? The data that you're trying to remove here, return, I should say. The data that you're trying to return doesn't exist. Like we could even say like the data you're trying to delete does not exist, right? Because we iterated through the whole list and we did not find it. Otherwise, if the iterator.next is not null, right, that means that we did find the data that we're looking for. And so then this is where that nice, wonderful little reconnection happens. But we can essentially say previous dot next equals iterator dot next. And so it's a little bit funny, but let's go back to our diagram here. Let's say that we're on this node, right? We did this iteration and we're on the one, we're in that spot where we exited that while loop, meaning we either reached the end of the list or we found the node that we want to delete. And in this case, it's the second one. We found the node that we want to delete. It's this one, right? And so we're like, great. Luckily, we've been tracking this idea of the previous node, and the previous node is this one, right? So knowing that, we can then say previous dot next, which is this one. This is the previous one. Lost it. This previous node dot next equals iterator.next. And the iterator is still on this one because we found the data that we want. And this iterator has its own next, which points to this one. So we're saying previous.next equals this one, right? So it skips over the current iterator, therefore removing that element from a list. Does that make sense? I'll pause there for a second if there's any questions.
Just a question here. If the data is in the last element, then .next will also be equal to null.
Which is a great point, right? So that was actually something I was just thinking about in my head, like, okay, we need to deal with the last element, right? So the inside here, if iterator.next equal null, it's a little bit tricky, but we could say while iterator.data does not equal data and iterator.next does not equal null. So we'll only exit this while loop unless we've found the data or iterator.next equals null. In here, let's say we found the data, but it's at the end of the list. So then we can say previous equals iterator equals iterator.next. So this right here could be a problem if iterator is the last element in the list, right? So then we could deal with that right there, where we could say, maybe we take this out. We could say if iterator.next equal null and iterator.data does not equal data, right? Meaning we found the end of
the... that out, wouldn't the first while loop end up being a infinite loop if the data is actually not in the linked list?
It would give you, it wouldn't be an infinite loop. It would give you an error whenever it tried to dereference that null pointer, trying to get to iterator.data after iterator pointed to null.
Jürgen, great points. This is the beauty of a live demo. So we'll leave that in there. Iterator.next does not equal null. That's a good way to get out of the loop. And then here we can say if iterator.next is null and iterator.data does not equal data, that means we did not find it, right? Then we could throw another else in here where we could say else if iterator.next equal null and iterator.data does equal data, meaning we have found the data and it happens to be in the last node of this list. Then I would just say previous.next equals null, right? Essentially cutting off this last node of the list. Does that make sense? Any other questions there? And we'll do a little testing. I'm sure we'll find some bugs with the live code here. But so this essentially says, and I'll just kind of comment this. So list is empty, nothing to delete. This says the item they want to delete is the first element. This basically means it's not the first element. Start iterating. Don't modify head ever. When you're iterating, you do not want to say head equals head.next, right? Or like we do with iterator equals iterator.next, because in doing so, we've just modified the list while trying to find something within it, which is why we create this iterator. It's essentially just a copy. It's another reference to this object that's currently head, and we use that to iterate so that we don't affect the head at all. And then because we may need to delete from the middle or end of the list, we want to track the previous. Cool. Then start iterating. Until we find data or reach the end of the list. When we exit this list, when we exit while loop, we have found data or the end of the list. If it's the end of the list and the data does not match, 404, not found. If we found the end of the list and the data does match, delete last element. Otherwise, we found data in the middle of the list and need to prune it or delete it. Does that make sense? Any questions there? Cool. So let's kind of let's create a couple of other kind of simple utility methods. So I'm going to say public void print. And in this one, I'm just going to, again, check if the head is null, head equal null. We're just going to sout the list is, and by sout, I mean system.out.println or print log. The list is empty. And I can just go ahead and return after that. Nothing else to do. Otherwise, again, we're going to create an iterator, or I should say node iterator equals head. And then I'm going to essentially, might as well just, what should we do? Let's go ahead and print that out. So I'll say out iterator dot data. And then we could say while iterator dot next does not equal null. Let's go ahead and just print that out again. And then we'll say iterator equals iterator dot next. So let's see if we can already have a little bit of fun with this, right? We've got the ability to add to the front, we've got the ability to add to the end, and we've got the ability to remove elements from this list, and we've got the ability to print this list. So over here in my main class, I'm going to create an object of this custom linked list class of type string. I'm going to call it my linked list equals new custom linked list. And I'm going to just say my linked list dot add front hello, my linked list dot add end. See if this works. World, my linked list dot print. We added this to the front. We added this to the end just for fun. So it should print hello world. Just building here.
Drum roll, drum roll, drum roll.
You should actually on a live demo have place a bet to see if it's going to work or not.
Yeah. So we got hello,
really down.
hello. That's a little funny. So I'm going to put a little breakpoint there and I'm going to debug this and see why it printed hello, hello. So we're here in the debugger. And if I look at my linked list, head points to hello, which has a next, which points to world. So the list looks good, but my print method looks bad. If we just got rid of this, well, iterator.next does not equal null, system.println, iterator.data, iterator equals iterator.next. Maybe.
You didn't move the next. You didn't actually move the iterator. So if you swap the iterator.next and the system out in the sequence of it, when you print it out.
Oh, because world.next equals null.
Yeah.
So we could
But you do need to have a system. Yes. Yes.
all right. Hello world. So that works so far. And then just to be, let's just keep adding things to the front, which is, the fastest way to be doing anything here. We'll stick with our hello world, yay. So this should print out yay world hello, right? Because we added hello, then we added world, then we added yay, and they all got added to the front, which is a really, really fast operation, right? And we can see that it did print out yay world hello. And if we go back into the debugger, and if you guys are, especially for the Java folks, if you're not using the debugger already on a day-to-day basis, I really recommend that you do, because you can just set a breakpoint like this anywhere in your application. It'll stop you there, and you can look at the current state of any variables that are in your application. So here we have this idea of the head node. It's got data, which is yay, and it has this next element, which points to another node, which has the data world, and a next element, which points to another node, which has the data hello, and the next element is null, right? So that all looks good. Now, let's try some deleting, right? So let's try to say my linked list dot remove the hardest one, which is world. And then we'll do my linked list dot print again to see if it worked. Here comes the drum roll. So it should print hello, yay. No. All right, so let's see what happened.
Well, it actually did.
Oh
Yay,
yeah, because I
hello.
printed it here. Yeah. Sorry. Yay, hello. Yay, it worked. Okay, so now let's try just removing the first, or I guess this will actually be the final element in the list, because we added it first, but we added these two things in front of it. So now it should print yay world. Nice, that worked. Now let's try to delete yay. Should be the front of the list. World hello. So there we've just validated that we can add, in this case, we're adding them all to the front, and we can delete from the beginning, the middle, and the end. Does that make sense? So a couple of other, with a couple of minutes that we've got left, it can be really nice to have, for instance, a size method. In any kind of data structure, it's nice to be able to very quickly check the size of it. So I could just say int count equals 0. If always checking if head is null, if head equal null, return count, which is currently 0. Otherwise, create an iterator and then say while iterator dot next does not equal null. Here, I think we could say butterfingers this morning. So if it's not empty, we're going to create our iterator so that we can iterate our way through this list. We're going to increment count because we know we've got the head. While iterator.next is not equal null, enter this loop, iterate, and increment the count. And then at the end, return count. So that should work. And then it can also be really nice to have a method like contains, right? So this would be a Boolean contains, and it's going to take in t data. Again, if head equal null, we could return false because it's empty. It doesn't have it. Otherwise, this might start to look a little redundant. Node iterator equals head. We could just go ahead and start if head equal head dot data, or why don't we just use the iterator? While iterator dot if iterator dot data equal data, return true. we did find your data. It happens to be at the very front of the list. Otherwise, while iterator.next does not equal null, iterator equals iterator.next. Here we could do a little if right here. If iterator.data equal data, return true. So if we happen to get on the data while we're in this loop, go ahead and return true. If we get all the way out of this loop, that means we did not find it, return false. Right? So now we've got this idea of this contains method, which will iterate through this linked list, looking for the data and just return true or false if it finds it, right? So over in our main class, we could say something like Boolean b1 equals my linked list dot contains, let's say world. And then we could sout b1. And when this runs, we should see true print out at the end. And we did. But if I said my list linked list dot contains worlds, for instance, false. And then we could also say, for instance, sout my linked list dot size, and that should print out 2, because we added 3 things and removed 1, so there's still 2 in there, right? I know we're right up on time, and I've flown through a bunch of code here. Hopefully it wasn't so fast to be completely gibberishy, but I'm very happy to kind of stop talking and do some more explanation about what we've done here. And I'll also very quickly, we have, we already kind of talked about this, but we talked about removing from the middle and then removing from the end. We're just going to iterate to the end. We want to remove this last one. All we essentially do is cut off the pointer that points to this last node. And then we've essentially removed from the middle. All right. Who's got questions? How can I help?
Open this up to just about anybody. If you want, if there's something you want to comment on, something you want to ask, now's your chance. It's like most of the folks were there was some stuff back and forth. Jürgen was obviously active there. We did have some people who are looking forward to reviewing the content later when it goes up on YouTube.
Nice. Yeah, Alex, we will be posting this up to YouTube. A couple of other, and feel free to yeah, nice. Good to hear, Scott.
That's great,
Scott says
Scott.
Java isn't too intimidating anymore. Thanks, Ryan. So one thing I would mention here, right, is that especially as you get more comfortable with coding and this idea of data structures and linked lists, we've essentially made this up as we've gone. Like this idea of addFront or addEnd or contains or size. These are just utility methods that I've created here because I wanted to, right? But they all still enforce or conform to the idea of what a linked list is, right? And a linked list is just a list of elements where each element may or may not point to one other element. At least this is a singly linked list, right? So what's cool here is that, and I mentioned that I would talk about stacks or queues, is that let's just say that all I ever do is add to front and pop from front, right? What that is a stack, right? A stack is a data structure, and you can use any underlying data structure. You could use an array, you could use a linked list, you could use whatever you want that makes any sense to you. But this queue, because it's just a list of sequential elements, a stack is a first in, last out data structure, meaning just like a stack of plates. Whatever the first plate you put down will be the last plate you get out of that stack, right? If you put down 5 plates sequentially, that first plate you put down is on the bottom. There's 4 plates on top of it, right? And as you put plates onto the stack, you always put them on the top. And as you remove plates from the stack, you always remove them from the top, right? And now you can see that just by using, and for instance, right here, I could say, my linked, what did I call it? Custom linked list. Let's say of type, just for fun, let's change it up. Let's use integers. And I'm going to call it my stack equals new custom linked list. And now if I say my stack dot addFront, let's just use some numbers. My stack and then I could say something like, for instance, int x equals my stack dot popFront. Let's just do like ABC. I'm just going to comment this stuff out for a moment. Now, because I've just used the addFront and popFront methods, that means all I've allowed myself to do is add things to the front of this list and remove things from the front of this list. Or if you change it from front to back to from top to bottom, just take the front and the back and make it top and bottom. All I've allowed myself to do is add to the top of the list each time and then pop from the top of the list. So if I look at my stack, I popped them all. It's empty. But A equals my stack dot pop front. So A is 30, right? You can see that down here because 30 was the last thing I added. And then B equals my stack dot pop front. Well, the next thing in the list is 20 because that's the second thing that was added. And then C equals my stack dot pop front. Well, C is going to be 10, right? Because now we've made it to that bottom plate in the list. And so this is why I say, like, with linked lists, they lend themselves very, very well. It's a little confusing we've just created a linked list and now we're calling it a stack. It's because the behaviors overlap a little bit. And a linked list and a stack and a queue are just these ideas. A queue is the same exact kind of thing as we've just done here with a stack, but instead of only adding to the front and removing from the front, we add to the back and remove from the front, just like you would queue up in line at a movie theater. You get in the line at the back, and it's always the next person in the front that gets to leave the line, right? That's called a queue data structure. If I wanted to create a queue here, all I would need is to use the addEnd method and popFront method, right? Because that will add all new things into the end of this linked list, and it will only remove things from the front of this linked list, therefore essentially creating a queue, right? Which is a little bit confusing, but just to give you a little bit of a teaser or preview, linked lists perform very, very well as the underlying data structure for both the stack and the queue. So I will go ahead and stop talking in circles here. I hope that this has been useful for you all. If you have any other questions, please feel free to reach out, email, Slack, forum. I will share this code on GitHub as well as the video on YouTube, and we'll share that around. Please feel free to reach out if you have any other questions. John, any other thoughts or things I should mention while we're here?
No, I don't think so. We have one question about whether or not linked lists are related to binary trees. They are in the way that linked lists and binary trees are both dynamic data structures. They have a node and they have links to other nodes that are there. The difference there is that the linked list usually only has one link to the next item in the list. The binary tree actually has two links that goes to the left and the right-hand branches that branch out underneath it. And we'll do something on binary trees soon because binary trees are a great data structure, great thing to learn. Really good for sorting stuff. We also need to get some time here for stacks and queues because stacks and queues really fit into the algorithm type of thing. Why would you use a stack? Why would you use a queue? And how that can help you actually solve some really tricky computing problems. So I think that's a great two really good tech talks coming up. More data structures, more algorithms as well. So
yeah, absolutely.
So I want to thank you for taking this on. I mean, this was this was great. I enjoyed this. I learned a lot walking through this. If you've used any of the list objects or classes in Java, this is how they are built. We basically built our own little list thing. Ryan just did the exact same thing that the Java developers did a while ago whenever they created their first lists. So back in the day when I was learning it, I learned in C. C doesn't have a list structure. I got to make it myself. So this was great. This is kind of a throwback for me and lots of fun to watch. So Yeah, like Ryan said, if you have questions, fire them off on Slack. We're always there. We'll be back in 2 weeks. I believe in 2 weeks we have this is actually going to be two of the mentors, Galad and myself, and any other mentors that happen to be there. And we're actually going to be doing more live coding. We're going to be trying to solve some of the problems that are some of the lab examples that are there in the Java and the Python curriculum. We're actually going to be trying to solve them ourselves. So this ought to be fun to see if we're actually, do we actually deserve our jobs? This is the
Yeah.
chance for you to come in and see if we actually do. So
Nice.
other than that, Ryan, any closing thoughts?
No, just keep on coding, everybody. Feel free to reach out, keep pushing. And these data structures can feel really weird at first, all these pointers and next and previous. And when you get into trees, left child, right child. But to double down there, the binary tree in conceptually in many ways is very, very similar to this linked list. It's just instead of dot next, we have dot left child and dot right child, right? But also, I completely agree that's going to be a fantastic concept to cover in an upcoming tech talk. I appreciate your time, John. I appreciate you all coming out. Thanks, Ben. Thanks, Alex. Thanks, Giuseppe. Thanks, Jared and Bosa, Jurgen, everybody. It's been a pleasure. Enjoy the rest of your day, and we will all chat soon.
Right. Thank you. Talk to you guys later.
Bye-bye.
Thanks very much. Cheers, eh?
Yeah, thank you, Jurgen, for all your help too.
Yeah. Thanks for chiming in.
Hey everyone, thanks for watching. If you enjoyed this video, please let us know by liking and subscribing. If there's another topic that you'd like to learn more about, leave us a comment. We would love to hear from you. And if you want to become a coding pro, visit our website at codingnomads.co. See you next time.